So yeah, Parsley basically was my baby, my master's thesis. It's since spiraled wildly out of control. Sort of give a bit of background, I did my PhD in parser combinators. I'm going to defend in December. And something that I experienced is every year teaching about parser combinators was watching students write the same parsers over and over again and just seeing how bad they were. And the thing was is that years ago, we didn't really know what we were doing. It's like people always wrote about parser combinators, but everyone was just writing their own library in every single blog post that ever existed. And no one really talked about how to actually structure them and write them. And so I dedicated time to that. Those ideas became the design patterns for parser combinators papers. And I'm going to talk a bit about some of those patterns today and sort of give a sense of not only what these patterns are, but also how Parsley has tried to embody them inside itself. And these are potentially lessons that other libraries can take on, or if you're working with other libraries, some of these ideas will be transferable. So what I'm going to start with, basically, is I've already written a parser. And even though Monica warned us not to do coding in front of people, that's exactly what I'm going to be doing. So I have written a parser earlier on this week. And I'm basically going to start by outlining what's going on with it, and then we're going to look at some problems, and we're going to refactor it. So basically, the language we're working with is a expression language, but it also has some statements. So we'll look at the expressions first, just to get ourselves familiarized. So we've got expressions which have addition, they have subtraction, they have multiplication, they have brackets and identifiers and integers. And all of the expressions are left recursive, and they have the natural precedence ordering that we might expect. And what I've done is I've kind of reflected that grammar directly into a Scala type. So every single sort of case in this grammar has been represented by a specific constructor in this ADT, or rather a hierarchy of ADTs, because there's sort of an implicit subtyping in the grammar that I'm leveraging here. And this is what we're going to be trying to pass into. So we're going to try and make a value of this data type. And similarly with statements, we've basically got a bunch of semicolon separated statements that can either be assignments, if statements, or skip, which doesn't do anything at all. Assignments are an equality or an assignment with an identifier and an expression. If statements don't have parentheses, we don't need those, but do have braces and else statements. Crucially, they always have to have else statements. And they're only allowed to contain comparisons, so they're pretty simple if statements. But that's basically what we're starting off with. And again, we have a syntax here which is represented pretty much the same, except for one, which is statements, which I've chosen to represent as a cat's non-empty list. This is one of two cats things that will appear in this talk. And this is just because we can't have the empty program in this language. So I've decided to represent that again with data by saying, okay, well, the list of statements that will generate is non-empty. So that's basically that. So the first task of any parser implementation is usually the lexing aspect. Now, parser combinators don't normally do lexing, right? It's usually scannerless is what they call it. So lexing just forms part of the regular language of parser combinators. There's no separate phase, there's no distinction. And there's a whole bunch of patterns that sort of surround lexing, and I'm not going to talk about any of them, because turns out Parsley hides them all for us. So basically, what I've got here is I'm leveraging Parsley's lexer functionality, which is allowing me to give a description of the language I'm working in, and it will do the heavy lifting of dealing with white space and the sort of conventions that are necessary for white space, and handling keywords and making sure keywords and identifiers don't clash, and all sorts of things. And it has, as Noel described it the other day, a many-armed octopus of descriptions, but that's okay. I'm basically saying that for spaces, I basically care about any white space characters, Unicode. I don't care about comments. I haven't got comments here. I've reserved the following 3 keywords as special in the language, so these can't be identifiers. And I've said that every other identifier must start with a letter, and then everything else can be letters or digits. And from these descriptions alone, Parsley is able to synthesize a whole bunch of different parsers and combinators that can work with these things. So in particular, I'm pulling out signed decimals. They can be arbitrary sized, they return big ints, and identifiers. So that sort of aspect, the identifiers and the integers, I've now handled that. The other thing that I'm pulling out is something called implicit symbol. And basically, that's allowing us to use Scala's string literals as parsers. So when you see a string literal in the rest of this code, you're seeing a parser that reads exactly that string literal, but also handles white space afterwards, ensures that it's not, part of an identifier or something else. So it's sort of doing this work for us. But that's the lexing aspect. So there's a whole bunch of patterns, but I'm not going to talk about them because they've been hidden by the library. That complexity has disappeared. So we'll start looking at the expressions then. And expressions are interesting because they have a natural left recursion in them, right? We can see expressions are defined immediately by having an expression on the left. Now, for those who are unaware, recursive descent parsers don't handle left recursion very well at all. They're basically infinite loop. Parsley is a recursive descent parser, so you can't just write these directly as they look in the grammar. Instead, there's a pattern for that, and that pattern is precedence combinators, or some way of describing a whole table of precedents. And that's what I'm using here. So I'm basically saying we have 3 layers of precedence. The first is we have plus and we have minus, they're on the same level. We have multiply, that's slightly tighter. And then we have bracketed expressions, integers, and identifiers. And the types of these different levels vary, and we don't need to worry about that too much, but Parsley has got an ability to help us stitch together the different types in a sort of sensible way. But we're starting to see some extra things here, right? So we're seeing as, and we're seeing map. Now, for those familiar with Katz's ecosystem, as is the as that you would have been familiar with. It's basically saying replace the result of passing this thing by this thing. So it's saying if we read a plus, that should be replaced by the actual as, the add constructor from our data type. And similarly, if we have parentheses, once we've read an expression, we wrap up the result of that expression in a parentheses node. So the key with parser combinators is that you have to be explicit about how you want to construct your data, right? It's not like a parser generator where it will just do whatever it wants. We're actually saying here is how each individual part of the parser stitches together to make the whole. And this is part of what we'll be refactoring. So these are a bit noisy, right? There's quite a lot going on in just this line. So we're trying to tighten that down and decouple these things. And then the statements are perhaps a bit simpler. So they're just relying on the classic combinators and one little bit of magic set by one that basically says, okay, we have statements. Here's a recipe for delimiting them by semicolons. Right, so we're going to read a list of statements, and they're going to be separated by semicolons, and we want that list back. In fact, it's going to give us the non-empty list from Katz. So what other things do we see here? Well, we see statement is an assignment, or an if statement, or a skip, and a skip should return skip. And we see the other part of Katz that I've got lying around here. So for assignment, that's an identifier. Also pass an equal sign and then an expression, and then map n them. So that's basically taking n different arguments of type parser and putting all their results together with the given function. So this one has 2 arguments. So this is a two-valued tuple. If statements have 3 arguments, 1, 2, 3. So that will be a 3-argument function that gets passed in. And again, these are a bit clunky. They don't look very clean with respect to the rest of the grammar. And the last sort of operators are these little arrows. And these arrows sequence 2 things, and they always point at the interesting thing. So if you're reading ifs, right, we don't care about the if token. That's not relevant. What we care about is the actual comparison that we read afterwards. And when we're reading statements in braces, we don't care about the braces. We can forget about those. What we care about is the statements. So we're all pointing at the statements. So this is the parser as it stands. And the sort of problem that I've identified here is that we've got these map ends. They're also written backwards. We've got the dot applies. It's all looking a bit noisy at the moment. So it's kind of close to the grammar, but there's like something in the way. And what I want to start with is basically I'm going to take this line and I'm going to do what I want it to be, and we'll try and figure out how to get there. So what I want to be able to do to this line is I basically want to be able to put a sign at the front. And this won't compile for now, so ignore the red squigglies. And what I basically want to say is that this, whatever this is, should be a function that takes parsers. They're passing some syntax, but we don't really care what they're going to do on the other side. And we want to find a way to construct the AST value with that thing. So we're trying to decouple two different things here, right? One is the parsing of the syntax, and the other is how to construct the results we want. So let's split it down the middle so that we can keep this line in mind while we go upstairs. And the place where I'm going to do this work is right over here. So I'm going to start by defining stumped, because it's in an enum, and then I'm going to make assign. So this is the regular companion object for case assign. If you're not familiar with Scala 3, this is a shortening for case classes, but they still have companion objects and they live in the sort of nested scope. So we're inside enum statement, so we have to be inside object statement, and then we have object assign inside that. And what we're trying to do is, well, we kind of want something that looks like a function here. And the way to mimic that is with an apply. So I'm going to shove in an apply here and hope that I can type correctly, because as we know, we can't type when someone's looking. So we have expressions, and what we want to return is a parser that returns a statement. So if I just leave it like this, it's going to compile again, so we've got something of the right shape. Now, how do we actually implement it? Well, if you sort of look at the delta between these two lines, what's the difference between them? Well, it's the map n, right? The map n has gone missing in the line below it. So that's basically all I need to do to fill this in with, is to say, well, okay, let's take v and we'll take x, and we will map n them with assign.apply. And that compiles, and that's it. Right? That's the first pattern that I'm sort of trying to describe here. This is called a bridge, a parser bridge. And this name comes from the OOP bridge, which is something that decouples two things from each other so they can vary independently. And what we've allowed is for the varying of the syntax and the construction. Now, on its own, it doesn't feel like it's particularly profound, but you could start doing things in here that are unusual and might really make the grammar look like a mess. So different examples of things you might be able to do in here are disambiguate between different structures. If you had similar looking syntax and you didn't want to backtrack to parse them, you could sort of parse the union of them and trying to decide which one it is by pattern matching. We might be able to enforce data invariances, so we might have some things that we need to be true that is really too hard to express in a grammar. So we just want to do it programmatically, and we can shove them in here. Or it might be the case that someone comes along and changes our AST, in which case we actually don't want to have to change the parser. If we can just patch this bridge so that it does the right thing, the parser doesn't need to change. And another good example is, say we want position tracking or position information incorporated. That can live in here, and the parser doesn't need to be littered with like fetching the position every literally 2 calls. So this is an example of a pattern that any library could do, right? You could, if you were a fan of catsparse or fastparse or whatever, they can all do this. What Parsley gives us is a shortcut to do it. And that shortcut is basically, it's sort of noticing that this has a very specific structure, and that structure is that it's calling another apply from the companion object, from itself, right? And so what I can do is I can pull in parsley.generic, and autocomplete is going to save me from typos. I'm going to pull in generic bridges. So these are an implementation of this pattern, but just made as like a self-contained little blob. So I can say extends parser bridge 2, because it has 2 arguments. One is an ident, one is an expr, and it returns a statement. And we're done, right? So again, it compiles. So all of this bit that I've just written, I've been able to just say, look, we know how to implement this. This is easily templatable. So why don't we just do that? And for the vast majority of cases, this might just work okay. You can play around with this and be happy. If you started needing something like position tracking, that's when you could basically just write your own versions of these. But these are a nice starting point that you can use and sort of develop from there. And just want to illustrate that this does indeed work. So I'm going to make sure I run this. And what I'm passing here is I've passed skip followed by an if statement, a skip inside and an assignment on the other side. And there's definitely a tree of some kind in there. It's not particularly easy to see. So I will pretty print it with a function I made earlier. And what we'll get is something that looks pretty much like what we started with, but some spaces have disappeared because the pretty printer doesn't account for that. So the parser is clearly working, right? It's done the right thing. It's given us something. We've been able to pretty print it back to the sort of original syntax. And I'm just going to basically hop over to my file where I've already built all of the rest of these. And I'm just going to pick them all up. So we can now assume I can basically just take all of these existing things. No point in me re-implementing them. I'll make 1,000 typos. So we'll pop them down here, and I can just comment this out. So ideally, you kind of put these somewhere separate. So they wouldn't all be in the same file. You wouldn't have your AST and your parser all intermingling. But I've basically filled in the rest, right? So I've got all of the others. And this is a link to a page on the Parsley wiki that explains this pattern and specifically the generic bridges and other ways they can be used and so on. So it sort of talks about that. So I can go and I can refactor the rest of this parser. So I can see that here I can switch to an if, align these things nicely, get rid of the map-n on the other side. And I can do something similar here where I put my comparison, I remove the map-n, and it's starting to look a little less noisy, right? There's still complexity there because we are building the results as we're going, but it's a bit tidier. And we can start sort of decoupling things, and it's nice. Skip I'm just going to leave as is because it's quite small. It doesn't really need this treatment. But we can see we've also found similar things in here, right? So every single one of these has like an add, an apply, a mul, apply. This one we already know how to deal with because we've already built something similar. So we can get rid of these. But what's the problem with the other ones? So the problem is that when we've been using this bridge so far, we've been applying the arguments right next to the thing that's been using them. So, you know, we could apply these things as actual arguments. And that's a luxury that we can't really afford in this parser because add is not being applied to arguments. It's sort of being left as a function. The type of this is parsley expr term expr, right? It's actually returning a function. So thankfully, what generic bridge has done is it's actually implemented a way of dealing with this problem as well, right? Because we still might want to decouple. We still might want to do some other transformations. A good example with these is you might want to factor it so that instead of having 3 different binary operator nodes, you might have one with an enum that says it's an add sub mul. And again, we don't want to have to change the parser to deal with that, but we could write these bridges that help, you know, connect the dots between our AST's implementation and our parsers. And so what the bridge exposes is kind of a method that works the other way around from as. And the best name I could think of was from. So you say add from plus, and the rest of that can go. And similarly, sub from that. And so what we've really lost here is we've lost these applies, right? So the rest is all the same, but the dot apply is gone. And the inference for this can be a bit more stable as well, because if you noticed, when I defined the bridges, what I did was I made them a bit more specific than perhaps they needed to be. So I could have actually said that this was an add, right? It does return an add, we know that. And the reason I've made them less specific is because it helps the type inference, particularly with the precedence combinator. In Scala 2, this is a real problem. And actually, the bridges help make the inference work nicer. Scala 3 just sort of handles it well enough. So it's not so important there. But I always get in the habit of being the most generic I can with these things. So that's basically the bridges, right? And that's the big main lesson that I wanted to talk about today. And hopefully you can agree at least that compared to what it was, it is a bit more clean, and it sort of matches a bit closer to the grammar than it did before, right? Now the sort of key ideas are just sort of there, and really all we need to know is we need to just learn about these specific ways of stitching stuff together. And this is why I really love parser combinators. And you know, what some of the cool things you could do to refactor this is you can start noticing duplicated code. In this case, this isn't so bad. It's the same thing twice. But we might see other bracey things. And we could write a combinator to factor out braces, right? This is something we can do. We can write functions that take parsers and return new ones. I won't bother to refactor that. In fact, actually I could. It's easy. Because the lexer already does it. So what do I need in closing? There we go, braces. So what I can do is I can take these, and with the magic of Control D, I can just shrink them together and say that they are braces of statements. So a bit more concise perhaps, sort of saying in words what the intent is as opposed to in symbols and grammar bits. So in the time I've got left, the sort of other thing I kind of wanted to touch on a bit was error messages. And what I've got for that basically is I prepared 3 examples of bad inputs. So this one misspelled else, this one missed the else, and this one has put a semicolon between the if and the else, and that's not allowed. So what do these error messages actually look like? Well, we can have a look at them. Here they are. So the first one, pretty self-explanatory. It says unexpected else, expected else spelt correctly. This one says unexpected semicolon, expected else. Fine, but we don't really know why. And again, unexpected semicolon, expected else. We don't really know why. I mean, the else is right here. So one kind of common strategy that handwritten parsers use to address this is they sometimes write parsers that parse bad things, right? Deliberately parse bad things. And the aim is that if you can parse a bad thing, you can make a really good error message tailored to that specific scenario. And in fact, Parsley gives us a tool to start doing that. So I'm going to pull it in. And this is the last thing we'll see. What do I need? Patterns. So what we can do is we can write a little fragment of parser that tries to encapsulate what's going wrong here. So we'll start by saying, well, the problematic thing in each case seems to be a semicolon. So that's something we want to see, for sure. And what we might be able to see as well is potentially we might see an else, or we might just see nothing at all. So I can just say, you know, I don't care. This is an optional else. What I can do with this is I can say verified unexpected, and I'm going to make it a function. I'm not going to use its argument for a second. But I can say something along the lines of, well, you can't have no semicolon after if, right? That's a poor error message, but you get the picture, right? String's a string. So if I put this in, say here, we're sort of saying, try and read an else. If you fail, try and work with this, what I call widget. And you have to be careful with these, because the more of these that you add, the more obscure the grammar gets, because this is not part of the grammar. It's kind of like these extra things. It's why I always keep them to a side, and I always give them a name like underscore no, just to make it clear what they are. But let's see what the effect is. Well, the effect on the first one is nothing at all, right? This is not a semicolon, so the error message just does not apply in this case. The other two, we actually just see no semicolon after if, no semicolon after if. And perhaps this one could be a bit better, perhaps this one could be a bit better. So what I can do instead is I can actually say, well, okay, what if we return true here and we return false on the other branch? And let's give this a name, has else, say. Now we can actually do a check. So we can say, if has else, then, so we'll be saying you can't put semicolon between if and else. Otherwise, we know that there is no else that comes afterwards. So what we can say is, all if statements must have else's. So what's the effect on the error messages this time round? So what we can see is, again, this top one, nothing's changed. There's no semicolon, there's no else, so it's not relevant. In this case, unexpected semicolon, expected else, all if statements must have else's. Seems good. And the other one, unexpected else, unexpected semicolon, expected else, can't put semicolon between if and else. And there's an if and there's an else. So we've gained contextual knowledge, and these error messages are very clear and they're very tailored to these scenarios. And you can just do this. If you realize that people are making common mistakes with the data format or something, you use this pattern to try and abstract that. And the type of this, by the way, is no semi has type Parsley nothing. So it's guaranteed to always fail. And if the semicolon and the else didn't succeed, it makes no effect on the error messages that come around it. That's one property we'd want from this pattern. It only makes an impact on the error message if it was actually relevant, which is what we've seen in the first example. So that's basically all I wanted to talk about. I've shown these two ideas, the bridging that can help separate the construction of syntax from the actual parsing of it, and can help hide all sorts of complexities. And I've shown how we can make use of special combinators to help refine our errors. And in fact, you could implement this in cat's parse or fast parse in some way, but it's helpful that Parsley provides a combinator to help us short-step that. Thanks.
Especially, I like your approach with this predefined anti-buttons that users can. But we had similar issue in our project right now we're working on, and apparently, what we figure out that users don't want to have the first or the last error, which they usually have. They want to have all the errors at once.
Yeah.
So as I understand, apart from being awesome, Parsley cannot actually provide that. Or maybe
yes. So it's an interesting problem. So with semantic analysis, absolutely you want all of the errors all at once. With syntax, it's a bit tricky because where do you draw a line? So one thing you get from libraries that do support multiple syntax errors, and down the line, Parsley will support multiple syntax errors. It's definitely possible. It might require a little bit of intervention from the parser writer to sort of talk about how recovery can happen. Because one of the key problems is, what does a syntax error look like once you've already had bad syntax? Right, things get more and more deranged as the parser struggles to figure out anything. So what you can do, and the approach that I will take with this when I get around to it, is you put sort of safe points. So you could say in this grammar, a good place is saying semicolons are a good place to try again from. So you basically say if you have a critical failure inside a statement, just drop all the input until you reach a semicolon, then try again from here. And you can try making more error messages from that. But it's kind of a tricky balance because, yeah, if you just do it completely uncontrolled, the error messages can get insane very quickly and they become very irrelevant to what the actual problem was. But absolutely, yeah, for semantic errors, you always want them all.
Yeah, thank you. Probably it will raise complexity, just tenfold or something like that, but still
What, in terms of the performance complexity?
No, in terms of like, you know,
Or
code.
maintenance?
Yeah, maintenance.
So perhaps, like, depends on how many save points you want, right? If it's up to you, basically, how extreme you want to go with the error recovery. But
Thank you. Thank you.
Thanks.
Thanks again for a great talk. I have a question. So when we compile or run our code, we can see these errors. And as far as I understand, Parsley is in Scala 3. Have you considered using these like more lightweight macros from Scala 3 using inline and with the compile time ops error, where it would like highlight that you are passing the wrong expression like straight there with metals? Is that possible?
So that's the sort of area where my actual research blends in. So absolutely, I mean, for these kind of parsers, I always say that if the input is statically known, then it's a boring parser because you could have just put it in there. So dynamic errors are always a good thing, but yes, you can, if you were saying one library that I want to write soon is a regex library, and absolutely you would want to be able to report errors about the regex in your actual description of the regex when you were doing it. Something I did in my PhD was I used metaprogramming in Haskell to write a staged parser combinator library. And there's a whole load of different considerations you have to do that. But Scala 3's macros work basically like template Haskell, so it's portable, and I will be porting it when I find a shred of time. Especially as Parsley Haskell is enormous, and the porting will take some time. But it does really well, and you can basically generate handwritten recursive descent from these descriptions of parsers, and do analysis on them in the process and report problems like left recursion and stuff like that. You can pick them up. Although I do have a student project this year who's going to be working on bringing Scala fix integration to Parsley, so that will do some of this static analysis stuff on these parsers. But yes, it's a great question.
So it will suggest like fixes for your parsers.
Yeah, absolutely.
Oh, and then you can combine like with the Scala 2 1312, like compile like quick fixes, like where it's like separate from the Scala fix. It's the suggestions by the compiler with quick actions.
Cool. Yeah.
Looking forward. Thanks.
Thank you again for the great talk. I was playing with a different parser library for a pet project earlier this year. And one thing I was struggling with was, I think that library was returning, when I was chaining multiple parsers, it was returning a tuple 2 of a tuple 2 of a tuple 2.
Yes.
And like, I was in Scala 3, I was like, I know what to do here. I have the new tuples, and I wrote some of my own operators. I was wondering, given what I've seen, did you take advantage of polymorphic functions and those new tuples for Parsley? Or
no, at some point I probably should. So the caveat is that Parsley is cross-built. So it works on 2.12, 2.13, and 3. It's a nightmare to be in the intersection of these three languages, but I do it. That means that as far as these bridges go, there are 22 of them, and I wrote them all by hand. So yes, it's possible that you can extend this idea to work with the Scala 3 system. That's something I would love to explore. I might start having Scala 3 specific parts of the Parsley API moving forward.
I guess that was what the other, I think Cat's parse was also why they were doing it that way. Thanks.
Hey there. So might be a bit open-ended question, but do you think that bottom-up parsing will ever be possible? Given all of the quantum computing technologies that are coming out and making quite a significant change in parsing, especially when you have finite tokens and infinite sort of ASTs.
Well, bottom-up parsing is already very much a thing. So I guess in the infinite space, I don't know. Actually, I don't really interact much with bottom-up parsers because bottom-up parser combinator libraries are ridiculously hard to write.
Yep.
So I tend to stick with the recursive descent because I like the intuitive control flow. So yeah, I just don't know.
Cool.
So you gave The example of a parser bridge that you gave was like almost just better syntax around
Yes.
applicative, right? But you also mentioned using them to access like source code position.
Yes.
I was wondering if you had to hand just more examples of cool stuff you can do in a parser bridge.
Yeah,
as a-
absolutely. In fact,
Thank you.
so I mentioned this page. It is, you can find it on Parsley, on Parsley's GitHub. There's a link to the site. The wiki has 2 pages on bridges. One is for generic bridges in particular, because generic bridges don't handle source positions. That would require me making a decision on the user's part. I don't want to do that. But this does describe some of the additional use cases, like say, this is a great example, parenthesized expressions versus tuples. That may require backtracking because they share a lot of syntax, but actually you can write something that can disambiguate between the two without reparsing. So that's a cool application. Data invariances, like we know that Scala 2's tuples can only go up to 22 elements. Well, it's a bit of a pain to represent that in the grammar, but we can do it really easily with a filter in the bridge and just say, are there more than 22 of them? So again, we can start enforcing these things. And yeah, the only time not to use the generic bridges is when you need something like position tracking, in which case there's a whole other page that I can't access because I'm not on the internet. But there it is. Look at it. Zoom in on it. Oh no, it's gone. That also actually talks about how to build the bridges from scratch, and that actually gives examples of position tracking bridges that help incorporate position information into those AST nodes. So yeah, it's all somewhere in there.
Hello, great talk, thank you. I love stuff like this, but what I'd like to try and do is sort of frame it in terms of all of the lovely, hardworking commercial Scala developers who are here.
Mm-hmm.
Have you given any thought to how you get them to convince their managers to let them write a parser at work? What would they be using it for?
I mean, I don't understand why anyone wouldn't want to write a parser at work. So it's a difficult, I don't know, I guess it depends, right? Most of the time, JSON suffices or something like that. But if there is a data format or your company is working on its own DSLs or stuff like that, then absolutely that's your in, right? You want to do that. And you can especially make that case. So if it's a choice between parser generators or combinators, all of the same advantages for handwritten parsers, which are used for basically every compiler in the world, apply to parser combinators. So stuff like the good error message support, which we've seen, right, how that comes about. Parser generators don't really have the information to do that in an easy way. And you know, the sensible control flow, the debuggability. There's debuggers for Parsley. There's even a graphical debugger that will land at some point. So that's how I would sort of justify it if I was in a position where we did need something like a parser. But I'd also say there's no reason to invent data types for the sake of it if a parser isn't required, right?
There was one more question here.
Hello, thanks for the talk. Given infinite time and money, what problems in this space of parser combinators would you work on?
Wow. So the last remaining bits of my thesis that I didn't finish off perhaps would be a start. That would involve, firstly, bringing my PhD work to Scala and working on the metaprogramming aspect. There's a lot of interesting stuff there because Parsley does a lot of optimizations to try and limit the sort of cost of building error messages. But actually, if you have the metaprogramming, you can analyze the grammar such that you can hard bake the error message string before parsing even happened, right? No need to carry around data. So that's something I've wanted to work on for years, and I never found the time, and eventually have to abandon it to finish my damn PhD. So that's something I would work on. And I guess, yeah, I'm always seeking to work on those ergonomics and the performance aspects and stuff like that. There's a lot still to do. I think one highlight of my PhD is always, whenever I submit a paper on parser combinators, the reviewers are shocked that there's still things to do with parser combinators. So yeah, there's lots that I would continue to do, basically.
Thank you.
Would you mind explaining what a parser combinator is, please?
It's a fair question. So the combinators are basically, very simply, this thing, right, which is, we've seen, they're all over the place. That's a combinator, and that's a combinator, that's a combinator. And it's a very fancy name for just a function, which doesn't have any like captured variables. So what it is parser combinators are a paradigm where parsers are just first-class values, and they can be manipulated as first-class values. And the combinators are functions that take these values and return new versions, right? So set by one takes a parser and returns a new parser that sort of combines them in some interesting way. And that's it, right? So parser combinators is just this idea that you can compose small parsers into bigger parsers with some recipe for how to combine them. I should have mentioned that at the very beginning. It's a problem with being an expert.
Thank you for explaining what a parser combinator is. Just above the parser combinator was what looked like some kind of string interpolation thing, a BNF. Is that essential or required, or is that just like commenting almost?
Okay, so what is this? This is I'm going to break the fourth wall. Here it is. It doesn't do anything. The reason I did it was because the comments are slightly harder to read in this font. So I decided to just hack it to make it into a string literal that can be read. I was not expecting anyone to notice or ask about it. But yeah, it does nothing at all.
Okay, I was wondering what it did, and the answer is it does not. Okay,
Yeah.
Thank you.
Right, I think we have to wrap up, but I'm sure he can answer questions afterwards. Thank you so much. Let's
Thanks.
give him another round of applause.
Okay, thank you very much.